Yeah, welcome to our CNS Tech Talk Thursday. Oh, my clock, sorry. I'm very happy to have today Yves Fauser from AWS Specialist Architect in Networking on the stage, who is talking about architectural patterns, distributed versus centralized. First, for everybody who don't know us, we are a independent cloud network and security community. You see our homepage, you get some more information about us. And here's also information about our next meetups. We have on the 18th of April another remote session from Michael Weisgerber from Fortinet about multi-cloud connectivity. And then we have an on-site meeting on 18th of June. Regarding the ground rules, please ask your questions after the session. You can ask in German or English, that's not a problem. But we want to provide the session also on YouTube, so please ask, as I have mentioned, after the session. So with this, I will hand over now to Yves.
Okay, thank you, Jörg. How do I share? Share screen. You cannot share. Okay, I think you need to stop sharing. Here we go. So now I'm unmuted. So yeah, hi everyone. I'm Yves. It feels a bit strange to introduce myself because most people know me on this call, but since it's being recorded, let me introduce myself. I'm a networking solution architect at AWS for the DACH region. So everything that is German speaking, and also help out with the Eastern European regions. And I do networking the whole day at AWS. And so this presentation is about how to do ingress and egress patterns and cross VPC. So how to, like what option we have for those patterns. And I will explain a bit what is meant by ingress and egress and across VPCs in the following slides. So yeah, already covered the agenda in the introduction. We're going to talk about distributed and centralized architectures for ingress, egress, and east-west traffic. So in general, distributed versus centralized architectures. What is meant by that? Well, in the distributed case, you kind of repeat what you deploy in your cloud. In our case at AWS, it's VPCs, virtual private clouds, which include all the networking concepts like subnets, like gateways to the internet, so IGW, Internet Gateway, NAT gateways, all those things. And other clouds have other names for it, but it's the same. And so you can either go and say, in an account, you cookie cutter deploy one VPC after the other in the same way, all with their own network components to go in and out to the internet or to private networks, etc., etc. That also, of course, across accounts. So not just one account with a lot of VPCs, but maybe also, and that's in most customers, that's the case, with a lot of accounts with a lot of VPCs, right? The alternative to that is you go centralized, and you still have a lot of VPCs and a lot of accounts, but your network components like your egress to the internet, your components like NAT gateways, and maybe things like a direct connection to your on-prem environment is all done on a centralized account. And so what are the pros and cons of both of them? Well, first and foremost, distributed, and I'm going to talk about all of those points here. Distributed has great scale and great performance, right? You have separated components for each and every of your VPCs in your accounts. And so there is little sharing across your network components. how well does a centralized approach scale in terms of bandwidth, in terms of I don't know, connections per second or connection limits? Depends on the involved components, right? There is a lot of things that auto scale pretty well, and where scale is not a big concern. In other cases, you might have things like maybe firewall clusters or something where you have to be a bit more careful on scaling it upfront to the right sizing, right? And so it really depends on your design. While in the distributed approach, it kind of quote unquote comes for free. That is highly scalable. Resiliency, distributed model, everything is repeated. If you have a configuration problem in one of your VPCs, then that VPC has a problem. It's hard to find things where everything goes down. In the centralized pattern, usually components are highly available. Components are pretty safe, or you can assume that they are safe, that if something fails, then something will take over. But you can still have a pretty high impact if you do a configuration mistake. Like you can add a single rule that will drop traffic for all of your VPCs. To be fair, you could say that in a distributed world also. Usually you use some form of a automation. So infrastructure as a code, maybe like with Terraform or so, and you can shoot yourself into the foot with that perfectly fine also, right? You create one entry in your automation that adds your false security rule into all your VPCs, you have the same impact. But yeah, in that case, maybe the centralized model has a bit more is a bit more affected by those centralized mistakes that can be done. Costs, here it really depends. You need to calculate it on AWS. You need to calculate it. I'm pretty sure you also need to calculate things on other clouds as well. You in a distributed model, you have a lot of effects of repetitive components where you might add up a lot of monthly cost for that repetition. While in the centralized model, you might have more cost impact from involved components that might have a bandwidth-based pricing. And so now if you have those involved components where your traffic, it costs money, and you have that traffic for free in the distributed model, then the question is, what is more expensive? The traffic that you push versus the repeated cost of repeated things or repeated objects in the distributed model. Now, the biggest factor that always kind of rules and points to certain designs is really the operational complexity and the organizational structure of the using organization. What I mean by that is if there is a strong team that handles networking and security and enforces policy, chances are that the centralized model with its property that you have centralized components where you can put in your centralized policy is easier to integrate into existing IT and corporate policies than a distributed model where you need to give maybe a bit more autonomy to individual business units that have their own accounts and their own VPCs. And also, if you give them less autonomy, you need more distributed control with more distributed touch points. And so usually a centralized model works better also from an organizational structure and corporate existing corporate policies. Okay, enough of the general things, but again, in my practice, most of the decisions circle around those things. And so it always makes sense to clarify this before you go into any design discussion first. One quick fundamental, we are all networking people here, so sorry to bore you with that, but I want to just make it clear so that the rest is not too confusing if we talk about ingress and egress patterns. So fundamental, return traffic with load balancers. If you send something to if a client sends something to a load balancer, to the public IP of a load balancer, then what the load balancer usually does is it does a source net of the traffic, so that the return traffic is actually going back to that load balancer. Yes, I know there are on-prem load balancers where you can have the direct return, but even on-prem, this was, I would say, seldomly done. In most cases, we attract the traffic back using source NAT. So if the load balancer has a different path out to the internet, then the path that the instance, the target in the VPC would take if there was no load balancer involved, then you can have different traffic patterns depending on if it came through the load balancer or if it goes out directly from the instance. Again, something that I guess is pretty clear to a lot of you on this call, but I just want to make it repeat it here. Little side note, our network load balancer in AWS is a special one. It actually preserves the source IP in the IP packet that is sent to the target, but the return traffic is still attracted back to the network load balancer. So if you ever have the case where you think, hey, why do I see the original source IP of the client in the internet? And why is the traffic sent back to the network load balancer? Well, it's us doing that in the VPC. Okay, so we can do mixed designs. So we can either have a design where everything is quote unquote symmetric. So everything that ingresses to the load balancer, it goes through the same path as traffic that would egress when it's sourced from something within the VPC. Or we can have a centralized egress, but a distributed ingress. So we can mix and match patterns. And that's why in the following slides, I separated out ingress and egress patterns when I talk about them. So let's talk about egress first. Basic design, distributed and centralized egress. In the distributed case, pretty clear. We have our NAT gateways and our IGW. Again, in other environments, they call something else, but likely you have the same components. NAT gateway is a stateful, actually a PAT device, which multiplexes a lot of outbound traffic towards a single or a pool of elastic IPs, which then are reachable from the internet. So the traffic goes through NAT gateway, goes out of the internet. Pretty clear. I guess you all have played with that in some way, shape, or form. You can centralize it. In this case, you can attach your VPCs to a transit gateway in our case, or to Cloud WAN, which is another routing option. So you have a centralized routing function. And when now the instance in the VPC is sending some traffic, then it hits the transit gateway, is routed towards a networking VPC, like a centralized VPC, where you have centralized NAT gateways, which NAT the traffic out to the internet. And Ollie said he would paste the links. Oh, yeah, I see that he did that. So anytime you see a link saying white paper content on the top right corner, then our friend Ollie will paste it into the chat.
Done.
Okay, and this is how it scales. Basically, anytime you add a VPC in the distributed model, you duplicate the components. In the centralized model, you just attach it to the central routing device, which is Transit Gateway. Now, what the logical next step is is to say, I want to put some form of an egress filtering in the pass, in the egress pass. What would be the reasons to do so? Mostly to prevent exfiltration, and with that comes URL filtering. So you want to control what the compute instances within your VPCs are able to reach on the internet. Most firewalls, also our own, like the AWS network firewall, are supporting also TLS inspections. So they would terminate TLS and also look into TLS to see if there is anything accessed that should not be accessed. You can also bundle that with DNS firewall options to also already block DNS requests to malicious sites, something that is also often combined. Now you can also put IDS IPS in there. You would do that mostly to protect your own reputation. So if you are somehow taken over, then you could be the source of an attack, or if you have a malicious employee. So you want to make sure that if you lose control, at least you have some form of protection that you will not be the source of a DDoS attack, as an example. Now, with egress firewalling, you can use any kind of protocols, which is pretty nice. So IP, UDP, TCP, it's all supported through firewalls. Now, yeah, distributed design with inspection. I already talked about that, so I will quickly jump through it. One thing that I want to call out is, yes, we have our own firewall at AWS, but we also partner here. At least 2 people in this call that are partners of us, and we can chat with them also in the Q&A. One of the things that most partner solutions support is to exchange also the NAT gateway with their own NAT capabilities. So this is then an option in, I think most people call it a 2-arm mode, where you can put your firewall, your partner firewall, in a centralized egress VPC or centralized inspection VPC, and also have it do the NAT gateway function by having a second interface in a public subnet that has an elastic IP assigned to it. And then distributed egress, well, of course, you can also do your firewall in a repetitive way in all your VPCs. So there are partners out there that also have like smaller footprint firewalls that you can easily deploy over and over and over again in this distributed pattern in a let's say halfway cost-effective way. Okay, that's just a repeated slide. Sorry for that. Oh yeah, sorry, that was the distributed one. Okay, obviously in the centralized egress with inspection, what you're doing is your VPCs are sending the traffic through a transit gateway towards a centralized inspection VPC, where you then have your firewall that is egressing. So I get confused of my own slides. Sorry for that. One deep dive that I wanted to do is to look a bit deeper into how gateway load balancer works in our case. Again, here, I guess other clouds have similar concepts. I'm speaking here really just for our gateway load balancer and how it works with partner firewalls or any kind of appliances that are put in front of gateway load balancer. So what gateway load balancer does is it gets first traffic routed to its gateway load balancer endpoint through the route table of the source instance. So this source is in a specific subnet. There is a route table pointing with an entry to that gateway load balancer endpoint. What gateway load balancer then does is it encapsulates the packet, the original unaltered packet, into Geneve. So it uses Geneve, the Geneve tunneling protocol to encapsulate the packet and send the packet with Geneve to the appliance, so to the partner firewall. When doing that, it will calculate, it will add a couple of TLVs. One of the TLVs is the endpoint ID where it came from. It will also calculate a session hash. And if a transit gateway is involved, it will also add the TGW attachment ID. What is important to understand is this session hash. This means any flow that gets established from the instance to the partner firewall through gateway load balancer has a unique session hash. And now the firewall will do its job and either send it out on a second interface in 2-arm mode, or if it does an east-west inspection, it will actually, or if it does it in, and you will see that in a distributed model, it will actually send it back to the gateway load balancer endpoint. So 2-arm mode, it's just sending it out over another interface. In the 1-arm mode, it is actually returning the traffic, the packet unaltered to the gateway load balancer and with unchanged TLVs. And it's important that it adds the session hash so that gateway load balancer now can correlate where it came from and where it needs to send it to which endpoint and for which session. And now on that subnet where the endpoint is of gateway load balancer, there is a route table lookup that then sends it out to whatever the route table entry points to. So in this case, the firewall is really what we would call a bump in the wire. It just looks at the packet and then decides yay or nay. I will allow that traffic or I will not allow that traffic. And if it allows the traffic, it sends it back unaltered to gateway load balancer. Now, why am I explaining all this? Because there is a beautiful pattern which I call the centralized distributed model. Yes, it doesn't make sense to call it the centralized distributed model, but it's essentially what it is. So you have a lot of spoke account, a lot of spoke VPCs, and in those you have your gateway load balancer endpoints. So you create a gateway load balancer in a central networking account, and you expose those endpoints to a lot of spoke accounts and VPCs. And now when traffic is sent to that gateway load balancer endpoint in those spoke VPCs, then it's going to get sent to the firewall for inspection over Geneve. And then if traffic is allowed, it goes back and then it uses the distributed components to go out to the internet or to whatever it needs to go. So this is a good combination of both the distributed and the centralized pattern. Now, firewalls, yes, most customers are asking for firewall security, but there is also the model of doing that with proxies. It's not seldom to find it. Before we had gateway load balancer and all sorts of firewall technologies, this was actually one of the standard ways of doing things to do an egress filtering. You would put a load balancer in front of a fleet of proxies, like likely your favorite script proxy or something, and that script proxy is then sending the traffic out of to the internet, and you can do that in a distributed or centralized way. What is the benefit here is you have a caching layer. So if you have a lot of repetitive downloads, then this might actually save you costs. Now, you can solve those problems in different ways, like having your apt caches also somewhere centrally, put in caching layers that are independent of the actual like outbound internet traffic to avoid that repetitive downloads, using your container registry in the cloud instead of using one on the internet. So those are all things that make it less important or interesting to actually cache on proxies inside of cloud. Now, one design option or one tool that I want to mention here, again, that's a tool that we have. I'm pretty sure others have something similar, is a firewall manager. It's not actually managing firewalls. It's more a central point to enforce policies, baseline policies, especially for security groups, but also firewalls. Including some of our third-party firewall vendors, which right now is Fortinet and Palo Alto. And with Firewall Manager, what you do is you create a policy saying something like, there should always be a specific security group added to any kind of load balancer that gets attached in any VPC in your organization. With that, you can do a lot of distributed security and manage things in a centralized way, even without having a central firewall cluster where you do all this. So if you decide for a distributed pattern, then using tools like Firewall Manager, and there are certainly tons of third-party tools in the market that do something similarly. That's actually a good design pattern to do to enforce distributed security through a centralized management layer instead of forcing all the traffic to a centralized point just because you want to have centralized control. Okay, last thing, and I'll jump quickly over it, is VPC sharing. So one of the things that we have is shared VPCs or shared subnets. This is an interesting pattern that you can do things like egress. You can have subnets in VPCs in a central account and then share that subnet to the spoke account. So instead of the spoke account having full access to that VPC and to that subnet, what they actually see is a subnet that they don't own. It's owned by the networking account, but they can put a compute instance in it. They cannot attach any networking or anything along those lines. And so that helps building a pattern where the compute teams, the application teams are really only caring about adding compute, adding the application, and not caring at all about networking, just saying, this is the subnet, I put it in, and then everything is sorted out for me. So you can combine it with centralized inspection VPC and centralized security. And that's a pattern that works pretty well often. Because of this nature of being easy to use for the spoke accounts where you just have to add an instance. It doesn't work well for organizations where there is a lot of autonomy, and also in cases where you have a lot of automation that crosses account boundaries. Things can get a bit difficult because of visibility of tags. So the networking account, as an example, can't see tags on instances that are deployed on those subnets, which can be problematic for automation systems that I don't know, create rules based on tags or firewall rules based on tags. So this is certainly a consideration to take when looking at VPC sharing, subnet sharing. Okay, talked a lot about egress. I think I'm doing good on time. Ingress is actually, like, if you saw a lot of option on egress, then yeah, you will be surprised how many options there is for ingress. And that's a pie chart, and we could leave it at that, and then start talking Q&A. But yeah, no, that's just joking. Let me go through the options. So we have distributed options, we have centralized options, and all of them are related to, are you using an ALB? Are you using a firewall in between? Are you using something like an API gateway, etc., etc.? So let's go through that one by one. So first model is to use application load balancer, ALB, with a WAF in front of it. There is also the possibility to have the WAF functionality being done in the CDN, either being like our CloudFront or somebody else's CDN that includes WAF functionality, and then so you can have basically just the ELB in your VPC, and then WAF is done on your CDN layer. But you can also put WAF on the application load balancer in our case. Or you could obviously also put a third-party load balancer with WAF capabilities into a VPC. That's obviously also a possibility. Now, it has a lot of great capabilities. However, it is limited mostly to HTTP. So it looks, especially for IP source listing, at HTTP headers, X404 headers, etc. And so it's pretty much quote unquote limited to what you expose through a load balancer. Now, ALB is obviously an application load balancer, so it's used for HTTP, HTTPS, etc. So that's a good fit. But if you have any kind of non-HTTP protocols, then this might not be an option. One thing to mention is on the centralized side, yes, you can put an ALB with a WAF in a centralized inspection VPC in a networking account, and then send the traffic to spoke accounts. However, one thing to consider here is if you have any kind of auto-scaling groups, anything that is dynamically going up and down, the load balancer that is in your networking account will not have the visibility of those things like auto-scaling groups in the spoke VPCs. That's why you have to do a double ALB layer, a double load balancing layer, putting like one load balancer in the centralized inspection VPC, in this case an ALB with a WAF, and then another load balancer layer like an NLB in the spoke VPCs to do the load balancing that is scaling up and down. A common pattern is to put an ALB with WAF in front of spoke VPCs that run Kubernetes clusters that expose their pods through a service type load balancer. That's when we see a lot this pattern where you have an additional layer of ALB and WAF in front of this. If you are more in the API camp, if most of your users are not using web front end, but it's mostly things like apps on phones that do API calls. If it's more like also machine to machine, business to business communication, then API gateway is used a lot. Either our API gateway service or a third-party API gateway that would be obviously exposed to an Elastic IP or a load balancer. Now, in our case with API gateway, you can use a private link to go from the API gateway to a target VPC. Usually, then you go to an NLB, which as a network load balancer towards then your target groups. And what are the benefits on API gateway? Obviously, you can do a lot of things like authentication, authorization with JAW tokens. You can do MTLS. You can look at a lot of HTTP details, etc., etc. Everything that you can do on API gateway is used here, and then you can target your instance in the backend VPCs. Okay, then ingress to firewalls. Works both in a distributed way and in a centralized way. In the centralized way, there you will have to think of double ELB again. because if you come in through the internet in our case, the internet gateway, you hit the firewall gateway load balancer endpoint, you inspect the traffic. Well, what happens then? Well, you send it to a load balancer that then sends it to the backend target. You can also obviously send it directly to the backend targets through the firewall. If you would use something like NAT and elastic IPs on the firewall, this is also a possibility. If you notice here, there is either the transit gateway or the other the other icon here. This is actually private link. So you could also use what we call private link to expose the load balancer and the spoke VPCs into the networking account, and then send the traffic from the firewall through to that endpoint too. Now, what does it help you? Well, you will get any kind of IP protocol support. Like everything we saw before is HTTP based. With those firewalls, you can now look at any kind of IP, UDP, TCP based protocol that a load balancer or an API gateway might not understand. Okay, shared VPC, yeah, you can also combine things with shared VPC. You can have a centralized ingress on an inspection VPC, and then share subnets out to your spoke accounts. Perfectly valid to do that, and it just follows the same pattern that we saw with the egress case. Yeah, and then finally, we also have a service that we call AWS Verified Access. I know other clouds have similar or can have similar services. In this case, what AVA does for us is it exposes a public endpoint, so a publicly reachable IP address or IP addresses, just like ALB. The difference here being that it is able to do both authentication through OIDC and OAuth, but also authorization based on a policy language that is called CEDAR. ALB actually supports also authentication with OAuth, OIDC, but AVA will also, on top of it, give you a policy layer where you can do authorization based on the claims received by the IDP. And that's also a very good option for ingress traffic, especially if you want to protect applications in your VPCs that might not have the greatest built-in authentication authorization capabilities. So this is one of the options. And obviously, again, the market has many options for those kind of authenticating proxies. I'm pretty sure that also in the firewall model, you will find features in the firewall that are able to do something like that. Okay, east-west traffic, and I'm good on time because that's actually pretty quick, I guess. So option number one is actually the easiest one, which is just use the public zone. What is meant by the public zone is, well, there is the internet, yes, but there is also the internet part of AWS. So if you have your elastic IPs, what those are actually public IP addresses on our, and I just call it public zone. I don't even know if that's really a term that is used outside. So hopefully I will not get in trouble. But you can connect VPCs through that public zone without any problems, basically using internet traffic, but with a lot of bandwidth. So it's a good option. It, however, also generates costs because you get data transfer out on like a public interface through IGW, but it's absolutely doable. Now, obviously, since those public IPs are exposed to the internet, they're reachable from the internet and from other AWS customers. You need to be careful with that. You need to make sure that everything is authenticated and encrypted, and you need to make sure that that you have proper access rules in place. However, it opens up possibilities with a lot of nice patterns like overlapping CIDRs, because you can just repeat your VPCs. You don't care about overlapping IPs because everything happens on public IPs. Now, public IPs now costs money. If you have a lot of them, that costs a lot of money. So maybe it's really not the best idea to have thousands of elastic IPs being applied to each instance that you deploy in your VPC. So this really only makes sense if you use NAT gateway and load balancers so that you reduce your sprawl of IP addresses, or alternatively use IPv6. With IPv6, basically every IPv6 address is for free, and you happily route between them without any problems. Now, another option is VPC peering. VPC peering, you need to be careful because it's not transitive. In other words, you can't have a like a chain of VPCs going from one VPC 1 to 2 to 3. VPC 2 can't be a transit. It's not transitive. And so if you use VPC peering, you need to build like a full mesh of peers and add your routing to it. That's pretty cumbersome in a large scale. I have seen customers solving that with automation, but still it only works up to a certain point when it gets hardly manageable also in terms of quota that you have for VPC peering, etc. So what most customers then do is to centralize that through TGW that we will see in the next pattern. The other option is private link. And private link is used in a lot of cases when you have more of a loose coupling of businesses, maybe in an ISV scenario where you have a provider that is providing a service to a consumer in AWS, and so they want to offer that service through a private link endpoint. In this case, what happens is you create an NLB for your service, you expose that through private link, share the endpoint to the remote consumer account that then accepts it and then can reach your service over the NLB. That is perfectly viable also inside of one organization. A lot of companies actually doing that. And again, those companies doing that tend to be the ones that have a lot of autonomy between business units, so that this model works pretty well. That's a TCP-based technology. So right now, no UDP support. However, you can use any kind of TCP connection over this. Obviously not open to any port. It's not routing. It's like exposing one specific TCP port on an IP address in the consumer VPC to the NLB on the target side. But it's not limited to only HTTP. I guess that's what I want to say. Yeah, and then what we see most is Transit Gateway or Cloud WAN that we'll see in the next slide, which is able to interconnect all your VPCs through a centralized routing function, a layer 3 device that is also capable of being split into different route tables. Yeah, and I guess a lot of you already know what TGW is. It solves the challenges that you have with things like VPC peering, which is not transitive, and it gives you this centralized routing layer. And we saw earlier, coupled with a firewall, you can have centralized east-west inspection through a firewall in your centralized inspection VPC. So now traffic from one spoke to another can go through a firewall, be inspected there with any kind of IP, UDP, TCP protocol. Yeah, and again, this is a pattern that we see being deployed in a lot of cases, in a lot of large cases also, and works perfectly. And then finally, Cloud WAN, what is it? Cloud WAN is a policy-driven approach. It's from a routing perspective pretty similar to TGW. However, you don't interact with it through individual router components. You have a so-called core network policy where you define your segments, your attachments, etc. And then that policy gets deployed onto the edges on your network, which is your routing edges. And we have a lot of great implementations together with things like SD-WAN partners, firewall partners, etc., to steer and put traffic onto Cloud WAN. But that would be a whole different session. Cloud WAN is something that can be used nicely across regions. I don't have enough time, and I actually removed those slides that talk about inter-region traffic. I removed all those slides that talk about hybrid networking because we just don't have enough time. But Cloud WAN is also the best solution when you have traffic between a lot of regions. But it's perfectly fine and adds a lot of value also in single region deployments. And then we have VPC Lattice, it's the last option. And that is a layer 7 based service, which is very different from routing services. So very different, but also similar in a sense. You have also a centralized service or a centralized object that you share, which is the service network. And onto that service network, you can publish services. You can publish services out of things like Kubernetes clusters through a gateway API controller. You can publish services out of Lambda. You can also, sorry, 1 second. Okay, test 1, 2. I can speak again. Okay, you can expose your services also out of load balancers in standard environment where you use auto-scaling groups. And before I completely lose my voice, I guess I need to go to the final slides. So what did we not talk about today? Again, we didn't talk about multi-region. We didn't talk about hybrid networking. Didn't talk about DNS considerations. Didn't talk about CDNs, global unicast or anycast traffic, like our global accelerator. So there is tons of things. And sorry, we only had 45 minutes. But if you want to reach out, happy to have like private sessions with you and talk about more details. Now, big favor, please take the survey. Somebody will put it into the chat for me, I hope, but you also have the QR code. It's not just for me, we also have a couple of questions in there for the CNS, like if you would want to contribute to session in the future. Yeah, with that, I'm done with my session, but I'll keep that slide so that you can take a snapshot of your QR code. Cool. Yeah, Gerd, it's not my age. Actually, I had that once ages ago in a big presentation, and since then I always have my water or something to drink. It's crazy. Sometimes the voice is just blocked. I don't know why. Should we go over the questions?
Yeah, sure. We have a few questions. Let's have a look at the chat.
Can I have you not ask his questions also verbally? That makes it more lively.
Yeah, no problem. 1 moment. So Gerd is asking, what's a encapsulation inside with tags in VPCs?
You mean what the VPC encapsulation is? I'm not sure I get what you mean.
Yeah, because if you have tags, then you have to have a special encapsulation to transport these tags.
Oh, okay. I guess I understand what you mean. No, what I meant with tags is tags on resources. That's more like a management construct. You can tag things like instances or any kind of object on the API, so that you have metadata on your instances that you can do things with. Like one thing you could do is to use those tags to collect them into some form of a firewall group, et cetera, et cetera. That's what I meant with tags.
Okay, thanks.
Cool. Then we have a question from Einot. Is the service chaining service graph an option for ingress and or egress? And also, second question to this, have we any partner support for this, for service chaining?
Service chaining. Right now, we don't have an implementation that would allow us to do service chaining in another way than steering the traffic through route tables and route table entries. I guess that's the current answer.